vehicle controller, and then we're going to look at energy management strategy of HEV control, which is basically trying to optimize fuel economy. And section 2 have 3 bullet points. We're going to start with rule-based control, and then instantaneous optimization approach, and then horizon optimization approach. So when we talk about vehicle control, there are different algorithms to do different things, and I mean we call all of this, sometimes we call all of this controller, but when you look at more details, there are different parts, different modules within the controller, and this is just terminology. Okay, we sometimes call decision, sometimes logic, sometimes control. And when you say control, that's what we mean by usually it refers to automatic control, the feedback control kind of thing, control theory, right? And that's not everything. When you actually look at controller, it actually has a lot of logic, you know, if then else kind of thing. So if this happens, then do this, you know, if that, do that. And then you also have to make some high level decision too, depending on different conditions. And here in this, this is one example of logic, okay? This is engine start logic. When you start the vehicle, and we are familiar with this flow chart, right? If this, then do this. If not, then do that. You know, yes, no, right? This is how logic flows. Right? For hybrid electric vehicle, we usually have in this course, this is what we are going to focus on, okay? We're going to focus on control and decision. And usually control refers to low-level control, feedback control kind of things. But decision usually refers to high-level control, high-level decisions. And there is hierarchy within the controller. So for example, we have a driver, and driver asks for power, right? You know, accelerator and brake. And high-level decision maker or high-level controller will determine what to do from high-level, system-level perspective, and commands each low-level controller, which takes care of its components. So engine, motor, transmission, and the vehicle. So this high-level controller has to sort of supervise everything, right, and coordinate all the low-level components. So this guy needs to be smart, right? So this usually requires for high intelligent part of the controller, where a low-level controller is more responsive and making sure the command is executed. So if engine command was, produce, 100 Newton meter, then the controller try to make sure your engine produces that engine torque, right? So usually this is like engine torque, motor torque, which gear, and then friction brake. So this guy is very important. And in this course, we're going to focus on this controller, okay? And the high-level controller usually handles fuel economy, emissions, and drivability. It looks at longer horizon and takes care of relatively slower dynamics, because we're talking about energy flow, right? Whereas low-level controller takes care of transients, drivability, and some impact on fuel economy, and then emissions. And then, but they look at shorter horizon and closely related to fast dynamics, okay? And this is another view of power or energy management strategy. So driver asks for power, right? And the controller needs to do whatever it has to do to command gear, motor, and engine to provide this power while maximizing fuel economy, right? But this controller gets information such as state of charge and wheel speed, vehicle speed. Right? And servo loop or a low-level controller is with this component. And their job is to make sure it does what was commanded. This is command. And usually feedback control is good at this. Right? Reference tracking, disturbance rejection, right? And usually you need to design controller that such that Y tracks this reference. Right? Any questions so far? If not, Let's move on to energy management. So we looked at these three architectures or powertrain configurations, and we looked at series hybrid, parallel hybrid, and split hybrids. And one of the easiest and simplest approach for series hybrid is thermostat concept. I mean, it's almost useless, but still can do. Because we can operate the engine at any speed, right? So engine speed, engine operation is decoupled, mechanically decoupled from the wheel, right? So we can do whatever we want regardless of vehicle speed. So thermostat is possible because regardless of vehicle speed and vehicle conditions, we can just focus on state of charge. And if state of charge is low, then recharge. If we have too much SOC, then do not charge and just use battery. That's called the thermostat concept. 그 thermostat이라는 게 온도계입니다. 온도계. 그래서 뭐 뱅뱅 컨트롤이라고도 할 수 있는데 이제 SOC가 낮으면은 엔진 켜고 가장 좋은 효율점에서 운행을 하고요. SOC가 높으면 그냥 엔진 끄는 거예요. Do you think this is a good idea?
Isn't this essentially how they tuned the very first generation of the Volt and people kept complaining?
Sorry, let me turn. How do I turn off sound? Okay. Could you repeat that again? Sorry about that.
That's okay. I was commenting I remember vaguely that the first generation Volt, they kind of do it this way and people keep complaining because it's very alien. It's a very uncomfortable driving experience.
Uncomfortable?
Well, because the engines is completely decoupled from a drivetrain is one thing, but it's also whenever it's on, it's like drone at a constant high RPM noise that has nothing to do with what you're doing, with what the drivetrain is actually putting on the road. So it make people feel like it make them feel disconnected from the driving. It's like they could not gauge how the car is performing. It's very very unsettling from what people have been saying on very first test drives.
I see. So you're commenting on the driver perception, how driver feel. So if you completely decouple engine operation from driver demand, then yes, then engine will do whatever it needs to do regardless of your power demand. So sometimes that can be annoying. So for example, if you're asking for high power, but engine doesn't come on, but then sometimes you're not doing anything, but engine comes on. So yes, that's one of the downside. But what about from fuel economy? Can hear you.
Right. I think fuel economy would be good. In theory, you're always hitting the sweet spot. Like you never deviate. So the engine is always in the most efficient engines.
Well, so there are two parts, okay? Remember, this is series hybrid. So if you run your engine at its optimal operating points, engine efficiency will be super good. Right? But if you do this kind of thermostat concept, then all of your power has to go through the battery in and out. So that's a lot of loss. In addition to, all of the power has to go through the generator and then motor, right? But whenever you access the battery has also efficiency, right? It's not 100%. So if you have power flow through the battery, that means energy losses. But if you do thermostat concept, there will be large power flow in and out of the battery, which means you may accelerate battery aging faster, not just fuel economy. Okay, and then there's this concept called load following. What this is doing is in the big picture, you want to follow the load, meaning the engine should track, the engine should provide power demand, but we're going to put low pass filter to the power demand. So engine does not have a lot of transients. So engine tracks power demands in low speed sense, right? So any highly transient behavior in the power demand will be covered by battery and motor, because motor and battery is responsive, right? So if you have something like this, then engine will sort of do this. Right? And of course, you can handle SOC by adding this extra loop to handle low SOC and high SOC. So if SOC is low, you want engine produce more power. If SOC is high, then you want to reduce engine power and use some of the battery. Okay, so this loop takes care of charge sustenance. Okay, so back to this figure. Actually, we're going to talk about this soon, but there are 4 things. So we have to meet power demand. I'm sorry, 3 things. We have to meet power demand. We want to maximize fuel economy. And then we have to make sure SOC is sustained. Okay? And this is not easy, right? In other words, you must meet power demand, and SOC has to be sustained in the long run and optimize fuel economy. This is the optimal control problem of hybrid electric vehicle. Okay. And this is simulation results of thermostatic control. And what this is doing is, depending on the power demand and SOC, it'll operate on this line. Engine will operate on this line. And engine power. So when SOC drops, engine power comes on. Engine charges battery, and then engine turns off, and then SOC drops, then engine turns on. So this repeats, right? So we just looked at one of many control ideas, which was load leveling. But there are other smarter approaches, such as optimal control. So largely, we can divide it into 2 groups. First one is instantaneous optimization. Second is horizon optimization. And in all of this, charge sustaining is not explicitly considered in the optimization, and we need to somehow handle this. Okay? And comparison of control methods. So again, load leveling is engine centric, tries to optimize the engine, and it's instantaneous approach, meaning steady state condition, right? At certain speed, certain power demands, we want to optimize the engine, right? And there is vehicle level, system level optimization approaches, which is ECMS and dynamic programming. And ECMS is instantaneous approach. Dynamic programming is horizon optimization approach. There's also another approach called PMP, Pontryagin minimum principle, or variational approach. We will have a lecture on this sometime soon. I think maybe next week. And let's look at rule-based control first, okay? Rule-based control is usually designed by, smart engineer, right? With lots of experience, lots of, domain knowledge. and engineer will think how to optimize this with logic, right? For example, vehicle speed, driving force. This is vehicle attractive force, plane. So speed and force. So this is going to be maximum power. Sorry about that. And this is going to be maximum power provided by engine, right? And this is how much motor should provide. And at low torque demand, engine can do the job. When you need high torque, then motor can assist, right? So this is one of the rule-based controller for split hybrid, Toyota hybrid system. But anyway, what's happening here is that at low speed, low torque region, this is EV mode. Okay, and this is engine mode, and this is ECVT. This is also ECVT, but mostly mechanically driven. And this one, usually battery has to help, right? And then this purple part is, oh, I'm sorry, this is the part battery supports. And this part is actually ECVT mode, okay? But anyway, if you look at this map, this is mode map, right? So you can see which mode the powertrain should operate. So, and from logic rule perspective, we can come up with this table. Okay, when SOC is high and power demand is lower than EV power, then engine power is 0. But if SOC is low, then engine power should provide power demand plus charging power. Okay, and when power demand is higher than EV power, but lower than engine power, then engine produces power demand. But when SOC is low, then engine should provide power demand and charging power. When power demand is higher than maximum engine power, then engine power equals to maximum engine power. And motor and battery will have to help, right, to meet the power demand. So this is no matter what, right? Either case. And this is what Toyota hybrid, you know, controller looks like. So it gets all of this information, and the controller outputs engine throttle, speed, and torque. Okay. Oh, by the way, this is power split system, not parallel hybrid. Okay. But this still, this big picture, the overall controller scheme can be applicable to parallel hybrid too. It's similar conceptually, right? If you have a low SOC, then you should charge. If you have high SOC, you should use more engine. If power demand is low, then EV mode is better. If you have high power demand, then battery and motor should help, right? This can be designed based on engineers' intuition, right? Based on logical thoughts. And one can design these rule-based controller. If this, then do this. If that, then do that, kind of thing, right? Load leveling. This is I'm sorry. This should be rule-based control, I guess. Anyway, this is an example of a rule-based controller. How decisions are made. For example, driver asks for power, right? And if negative power is requested, then braking should come in, right? Region control. If driver asks for positive power, then there's control, the power blending, energy management controller has to command everything, right? Shift, engine, motor, everything. So this is the key part. And this, and then it also has to make sure charge is sustained, and we want to maximize fuel economy and meet the power demand, right? So this controller has to do is it has to determine how to split the power between motor and the engine. And then also how much we should recharge, right? So SOC part, right? So C is sustained. One logical thinking, simple control concept will be when power demand is low, then we might want to use motor only, EV mode, right? If driver asks for high power, then motor and battery should assist, right, to provide more power. And then when medium power is requested, then use engine. That's when engine is efficient, right? So such a process and such a you know, insight is not a bad idea, right? Because it's quite intuitive. 직관적이죠. 굉장히 그냥 누구나 들어도 로직을 이해할 수 있고 직관적으로 설계를 할 수 있고 엔지니어가 어떤 물리적인 해석과 근거를 가지고 어느 정도 논리적으로 이 로직을 설계를 했죠. 그래서 직관적이죠. So that's a nice part of the rule-based control. But is it optimal? That's the question. Probably not, right? And there's also controller, some people design based on fuzzy logic, but usually it's not that great. It's somewhere between logic and optimization. So it's not that great from performance perspective, but it's still somewhat logical or intuitive. Okay. So problem of rule-based control is, so it's a simple concept based on static maps, but it requires a lot of tuning and calibration to optimize the system. And even if you do so, you don't know its full potential. For example, let's say Yunte, let's say your boss, you're working at Hyundai Motors. You are asked to optimize hybrid electric vehicle, and then you tune, you design it, and you tune here and there, right? And then you improved fuel economy by 5%. Yes, that's a lot, right? But then next year, your boss asks you to tune it again. Can you improve it further? Or he asks someone else to tune it again. Can he improve it further? Right? How good is good, right? Is 5% improvement good enough? There's no reference, right? 그러니까 뭔가 개선을 시켜도 이게 얼만큼 개선이 됐고 개선이 된 게 많이 개선이 된 건지 적은 건지 한계에 얼마나 가까운지 전혀 알 수가 없죠. And this also means that if you have new vehicle, you have to tune and recalibrate everything again, right? But you don't know how close you are to the optimal solution. Is it good enough? How good is good? So it's a lot of tuning and trial and error. So that's where optimal control comes in, right? So optimal control이 이제 필요성에 대해서 얘기를 했고요. Let me see. Okay, I will finish after this concept, this slide. Okay. So there are different optimal control theories um, to manage the energy of hybrid electric vehicle, okay, to optimize fuel economy. And ECMS is one of the simplest but effective and provides near optimal fuel economy while still providing some intuitive algorithm. What this is, the main idea of ECMS is, by the way, ECMS stands for equivalent fuel consumption minimization strategy. Okay, and you will understand why it's named that way. Okay. The problem we are trying to solve is this. And then again, power, wheel power equals to power demand. And then final SOC equals initial SOC, okay? These two are constraints. And this is the original optimization problem, okay? But the main idea of ECMS is this. What this means is that it's hoping that this. So this was the original problem, but by having the minimization part put inside, now this problem becomes instantaneous optimization problem. Original problem was horizon optimization problem, meaning that you have to have a trajectory and integrate fuel consumption over time and then find the minimum, right? But if we take out, if we put the minimum sign inside, then it becomes minimizing at every instance, right? So we don't need to look at the whole horizon. Just focus on current states. Now the problem becomes simpler, right? Our system or make control decisions based on instantaneous perspective, but then we can also look at this optimal control problem from longer horizon perspective. So we're gonna talk about this today. We're gonna start with ECMS, okay? And we also addressed the limitations of rule-based control. If we, it requires a lot of tuning and calibration, and after after tuning and calibrating your powertrain for 1 or 2 months, you improve your fuel economy, but is that good enough? And what happens if your powertrain changes, or what happens your target vehicle changes? Your tire can change, your transmission can change, a lot of things can change. And if you have to optimize based on trial and error, then that's going to be very inefficient. And you're not even sure how close you are to the reference, meaning uh, performance limits. Right? So we are looking at optimization techniques, which gives us either optimal solution, and or we can use these solutions as a reference, meaning that how good is good, how close are we to the maximum performance. And we're going to start with a simpler concept, which is ECMS, which stands for equivalent circuits, no, I'm sorry, equivalent fuel consumption management strategy. So what that means is we are going to consider SOC, which is state of charge of the battery, as a future fuel consumption, and we can compute equivalent fuel consumption if we use SOC. Because if you look at this equation here, this is the cost function, the value function we want to minimize, right? And this is the problem, the optimal control problem we want to solve. We want to minimize fuel economy. But then there's also SOC constraints, right? And then power demand constraint, meaning that the vehicle has to provide power demand what driver requested, right? And final SOC must be equal to initial SOC, so charge sustenance. But these are not in the cost function, right? So we need to somehow handle those things. And how do we handle? That depends on control theories. And you will see how different control theories can handle these two things. So to handle charge sustenance, what ECMS concept proposed was, if we want to minimize fuel consumption, obviously the solution will be just use battery, right? Because using battery doesn't cost any fuel for now, right? But then we are using SOC, we are using battery, but to maintain charge, we will have to recharge in the future sometime, right? So using battery should also be considered cost. It's a future cost. We are not sure how much fuel we're going to need to refill battery, but it's going to be cost, right? Eventually. So that's the main concept. Plus, if we can focus on instantaneous optimization, then we can solve this more efficiently, right? So ideally, we are supposed to compute future cost properly and then minimize the total cost like this. But if we can somehow turn SOC dot, which is battery fuel consumption, battery energy consumption, and convert that into fuel cost, right? Then we can put that into here, and let's optimize instantaneous approach. That's the main idea. So now this integral is now outside, or this minimization algorithm is now inside of the integral, so we can optimize at every instance. Okay, so now let's go to 25. Now this is the new fuel consumption, or equivalent fuel consumption, which consists of true fuel consumption plus battery fuel cost. This conceptually makes sense, right? It's very intuitive, but the tricky part is we don't know this, because this is future cost. This is sort of virtual cost. In other words, this cost can only be determined if we determine what to do in the future, right? Depending on what we do, how we control in the future. So the way we can convert battery power, by the way, SOC dot is battery power, right? Do you remember? Battery model. SOC dot is current, right? So if voltage is known, then it's power. SOC dot equals, more or less, it's equal to power, right? So we are trying to convert battery power into battery fuel consumption, right? So we need to find out these values, right? This term represents a conversion coefficient, meaning that to refill this power or energy, how much fuel do we need to consume from the engine, right? And this term is just efficiency term, right? But we can make this, different. We can put different coefficients and make this model more accurate. But at the end of the day, this is just some lumped rough number, because in order for us to determine these values, we need to somehow average. We need some sort of average number, right? Because depending on how you operate your engine, the conversion efficiency changes, right? So it's not one-to-one relationship. And that's why I said we need to first determine how to control, and then we can maybe convert these numbers. But we don't know that. We don't know any of that. So we need some sort of average value, right? But average can change depending on control strategy. So this is a tricky part. And so we need to somehow come up with this number and then convert battery power into equivalent fuel consumption and compute total equivalent fuel consumption. Is that clear? Any questions? So to explain better using figure, this explains that. So we have a fuel tank, and when we use engine to 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 provide mechanical power, this is how energy flows, right? And if you get some help from motor and battery, then this is how power flows, right? Battery to motor and motor to the wheel, right? This is the vehicle, right? But what equivalent fuel consumption is doing is that if SOC drops, then you need to bring it back in the future. So that's this part. Some sort of virtual loop or connection. In the future, we will have to use fuel to refuel battery, right? Probably this power path. Is this clear? Any questions? So now we only have to optimize or minimize this value, right? Equivalent fuel consumption, which is summation of real fuel consumption plus battery fuel consumption. But battery value is somewhat virtual number or converted from battery power to equivalent fuel. So this is concept of ECMS. But later on, you will learn how this is related to the optimal control theory. So initially, this was proposed by, intuition, engineering sense, because all of this makes sense, right? This is explainable, right? But later on, we will find out how this actually is reflecting optimal control theory, which is math. We will find out the relationship between the derivation from optimal control theory and with this, intuitive approach. Anyway, so we have this function to minimize at every instance. But if we just fix this value, then that's just average number. We have we can use constant value. But if we use constant value, then the charge sustenance will not be guaranteed, because we don't know how the future is going to change, right? Driver might ask for high power, or you might drive highway or city. You don't know what's going to happen in the future. So if you use constant value of this coefficient, then charge will SOC will not be sustained. So this coefficient has two perspectives, right? It has a lot to do with optimal solution, because you're basically you need to evaluate the value of battery energy, right? Because you're converting battery energy into fuel energy, fuel consumption. But at the same time, depending on what value you choose, you are going to change your SOC trajectory, SOC change. So those two are coupled, okay? So for instance, let's say you use this as a very small number, then what's going to happen? You're trying to minimize this, okay? So we are trying to find U, control input, that minimizes fuel consumption, right? What happens if this coefficient is 0? Then what is the solution going to be?
So in other words, it's this is when the battery is completely depleted, right? And then it basically just stopped being a hybrid and it's just an engine.
I'm sorry, I didn't hear you.
So you say when that coefficient is 0, which basically mean that the battery is completely depleted. And if we just optimize based on this function, that means that we just ignore the hybrid part of the powertrain and just focus on operating the engine.
So yes, so it's correct, but the order is different. Order should be reversed, meaning that excuse me. So if this becomes a 0, then the optimal solution. So what this means is the battery energy is cheap, right? Battery energy is cheap. It doesn't cost you much, right? So you will choose EV mode, because even if you use battery, it doesn't have impact on the equivalent fuel consumption, because it's 0, no matter what you do here. Right? So you will choose U, that's an EV mode, right? Because it doesn't cost you much. SOC drop doesn't cost you much, right? But at the same time, doing so will deplete the battery. So it was the other way around. So you will choose because it's cheap, but then that means deplete the battery, right? What if this is expensive? then what's going to happen? Anybody other than Neil? 준태 학생 당첨입니다.
FSOC 개수가 커지면 그 엔진으로만 구동하는 그러니까 엔진으로만 구동하게 될 것 같습니다.
네, 그러면 SOC는 어떻게 될까요?
SOC는 점점 올라가다가 어느 상태가 될 때까지 증가할 것 같습니다.
네, 맞습니다. So the answer was the controller will use more engine, and that's going to lead to increase in SOC. That means battery energy is so expensive, and real fuel consumption, engine fuel consumption is cheaper, so much cheaper than battery, then you want to use engine as much as possible. And if in fact, if this coefficient is large, then you might want to even charge your battery, because if you charge, then this term will be lower. Anyway, so there is this charge sustenance issue, okay, and the solution changes, and these two problems are coupled, okay, depending on this term. So this term is actually the key to ECMS, okay. But the beauty of the ECMS is that once you find proper value of this coefficient, rest of the part is automatic. It's systematic. And I'll explain more about that in the next slide, okay? So choosing this value has a lot, like I said, choosing this value has a lot to do with charge sustenance, right? We want to maintain charge, state of charge near 50%, right? Which is efficient and healthy for battery, okay? And we also need buffer on the upper side and lower side. So 50% is usually good middle point, okay? And to do that, we need some sort of charge sustaining algorithm. And for ECMS, we can use something like this. So what this is doing is, for high SOC, you want to lower coefficients so that battery energy gets cheaper. And if SOC is low, then you want to increase coefficient so that battery becomes more expensive and use more engine. So you can, so if you are high, you want to deplete the battery, If you're low, you want to charge the battery. So you need some sort of this coefficient adaptation as a function of state of charge to ensure charge sustenance. Okay. So once SOC is determined, we need to find U that minimizes equivalent fuel consumption. How do we do that? Well, we have a model, so we need to do it numerically. We can also do it analytically, but it's going to be mostly nonlinear map-based equation. So let's take a look at this a numerical example. Okay. So in this example, power demand is 60 kilowatts. Driver is asking for 60 kilowatt of power, and SOC is 60%. Then SOC fixing SOC will determine this coefficient. Okay. So once this coefficient is determined, we need to now compute this and this, right? So that we can compute total equivalent fuel consumption. And like I said, this value, you can think of it as just SOC dots, okay? And put everything in this coefficient. So including the conversion numbers, okay? It's just some conversion coefficient, and there's really no point of separating those coefficients. It's just coefficient. So and we are going to adjust it anyway. So we can put all the coefficients in here, and this can be SOC dots, or let's put it this way, battery power. Okay. And now this is battery power as a function of engine power, which is control input. And this term is this one as a function of U. So if you take a look, with increasing engine power, fuel consumption increases, obviously. Right? With increasing engine power, battery power decreases, obviously, right? Because you're using more engine power, and if you use high engine power, you actually have negative battery power, meaning recharging the battery, okay? So if you multiply battery power with this coefficient, and then you add this plus this, then you get, oh, I'm sorry about that. So you convert using coefficients, and this battery fuel is this total cost, right? So if you add this term and this term, then you get this total equivalent fuel. And nicely, luckily, adding those two gives you some sort of convex function. So you have this nice convex function, which you can find minimum point, optimal point. Right? So this is U star, optimal U, which gives you minimum equivalent fuel consumption. So now you just need to keep record of this U star for given power demand and SOC. For this power demand and SOC, this is the optimal solution. Okay, so but you need to do this for different power demand and different SOC, so that you can actually drive cycle, right? Because power demand and SOC changes over time. So if you take a look at this plot, this is a summary, the final result of ECMS strategy, whereas z-axis is U star and X and Y is power demand and SOC. So U star as a function of SOC and power demand. Now this is an optimal strategy, optimal control policy based on ECMS. Is this clear? Any questions?
I do have a question on the implementation of this. Is this usually stored as a lookup table?
Yes. You can, but you don't have to. So you can also do this in real time if you have enough computing power, but probably it's a good idea to have a lookup table to save computing power, because you are solving this offline first and then just have the memory of that solution map.